In this last video of the first session of the course, we will perform a first implementation of the dimensional analysis by focusing on the kinematic condition at the interface between fluid and structure. This analysis will allow us to know if we can consider the fluid at rest or if the flow at infinity has an importance in the resolution of the problem. First of all, I remind you the set of variables and parameters of the problem. The important number leads us to perform a dimensional analysis to reduce the dimension of the parameter space. Our starting point is the kinematic condition. It imposes the equality of velocities at the interface between the fluid and the structure. To scale this equation, we can use the velocity u0 at infinity for the fluid. On the solid side, it is natural to use a characteristic dimension L of the structure to scale the displacement. As for the time, we can use the time constructed from a characteristic frequency of the structure, noted omega naught. This frequency corresponds, for example, to the natural frequency of a modal motion of the structure, for which we wish to study the coupling with the fluid. The dimensioning of the kinematic condition makes u0 appear on the left and omega naught L on the right. Transferring everything to the right side, we make appear a dimensionless number noted 1 over ur. Before analyzing the meaning of this dimensionless boundary condition, it should be noted that the length L that we use to scale the displacement psi is not equal to the order of magnitude of the displacement. It is psi naught. Thus, dxi on dt is not of order 1. Its order of magnitude is xi naught on L. And finally, introducing the number d equals xi naught over L, the order of magnitude of small u in this boundary condition is d on ur. The two dimensionless numbers we have introduced are called reduced velocity and displacement number. Now we can discuss the meaning of this boundary condition in terms of the respective orders of magnitude of d and ur. If ur is very small in front of d, then d over ur is very large, and this boundary condition shows that the order of magnitude of the fluid velocity around the structures is not given by the flow velocity, but is imposed by the kinematic condition. We can therefore make the approximation of a fluid at rest. On the other hand, if ur is of the same order of magnitude or larger than d, the order of magnitude of the fluid velocity around the structure is imposed by the flow velocity. We will discuss this general case in the course, but also the limiting case where ur is very large compared to d. In this case, the kinematic condition can be approximated by small u equals 0, which is nothing else than a classical boundary condition in fluid mechanics, zero velocity on boundaries. We will call this limit case quasi-static aeroelasticity. Before closing this video, let's try to physically interpret each of the dimensionless parameters we have introduced. First of all, we have introduced the reduced velocity. This parameter must be seen as the ratio of two characteristic times: the fluid time, L over u0, which corresponds to the travel time of a fluid particle along the solid, and the solid time, 1 over omega naught, which is the order of magnitude of a period of oscillation of the structure. Thus, the order of magnitude of ur tells us whether the fluid, during the time of its travel along the solid, sees a significant portion of the oscillation period of the solid or not. It should be noted that in the literature, it is often not the circular frequency omega, but simply the frequency f that is used to define the reduced velocity. There is therefore a factor of 2 pi between the two definitions. Sometimes it is the term reduced frequency that is used to define the inverse of ur. The other important number we introduced is the displacement number. It compares the amplitude of the displacement of the structure and a characteristic size of the structure. It will be useful later to know when we can linearize the equations. Finally, we have defined a number d on UR. This should be seen as the ratio of two velocities, the order of magnitude of the velocity of the solid xi naught times omega naught, and the velocity of the flow u naught. And it then appears natural to consider the fluid at rest if this number is very large. This is the end of the first session. In the following, we will consider the hypothesis of a fluid at rest. This will be the subject of session 2 and 3. Then we will study the case of the flowing fluid during session 4, 5, and 6. See you soon, and thank you for your attention.